So if we have a chemical reactions A plus a compound B, let's say this is aqueous, B is, let's do 2B, and B is gaseous, is now in equilibrium with C, which is going to be aqueous, and 3D, which is going to be solid. What's the expression of K equilibrium that I should write down in this particular case? What of C? Concentration or concentration? Okay, concentration of C times 1, because D is a solid, so you put 1 as your coefficient, to the power of 3, divided by A is aqueous, so I'm going to put the concentration of A times the concentration of B. Oh, sorry, B is a gas, so partial pressure of B to the power of 2. And more or less, this is what you've written down so far, right, for your class. And you can simplify it for, as long as you have solid or liquid, it's going to be 1. So usually you kind of ignore them. So far so good? Yeah. Now, the more generalized version, if you read your textbook, which is written to be much more precise, you should find this is actually, this is the final answer. But the initial step is actually, it's going to be written as the activity of C times the activity of D divided by the activity of A. Sorry, there's a bunch of A there. Times the activity of B to the power of 2. So this is actually the starting point. Now, these two are more or less going to be about the same as long as they're ideal. You know, activity of C is just going to be the concentration, activity of D, because it's a solid, is going to be 1, and then activity of B is just the partial pressure. So this is going to be the starting point, and they're going to be equal as long as the solution is ideal. Right. So whatever you've learned before with this newer syntax is the same thing, as long as the solution that you're doing behaves in an ideal way. So just an ideal case. So far so good? Yeah? Now, as always, what we're doing in quantitative analysis is what happens if your solution is not ideal. So what kind of correction that we have to do? And essentially, the activity constant that you've written down is kind of our way to cheat, because let's just say that because the solution interact with one another, the effective concentration is either going to go up or go down, and so on. And we're just going to sneak in a new constant, or a correction factor, if you like, of writing down gamma all over the place. That is, I'm going to sneak in some gamma. So these A here, A is activity, whereas gamma is activity constant. So basically, we're just going to multiply it by some constant on each one of our coefficient. So C is aqueous, so okay. So we're just sneaking a bunch of gammas here, and we're just kind of putting it right in front of each of the coefficient that you have before. It's just a correction factor. So I put it there. What I want you to notice is that the gamma, if it's to the power of 2, like this one, so the gamma must be to the power of 2 as well. That's why this one here is 1 times the activity coefficient to the power of 3, because as I've written down on the top, it's 1 to the power of 3 as well. So the activity constant is basically just a correction factor, because our solution is non-ideal. Most of the time, it's going to be pretty close to ideal, but once your solution becomes much more ionic, which is why you have to calculate the ionic strength and so on, this non-ideality term goes way, way up. So it becomes pretty big. So it's just our way to kind of sneak in a correction factor all over the place. There's a lot of different ways that materials could interact with one another. But majority of the time, we're going to be dealing with molecular chemistry. And if you have molecular chemistry, the major factor is essentially going to be electrostatic interaction. So the same reason, for example, water is highly polar, so that's why it doesn't boil as easily compared to, say, methane gas, which is nonpolar. The electrostatic interaction is going to govern your activity constant by quite a lot. So what and how can we get into that? And the derivation is actually going to be a bit more complicated, so I'm just going to go right into essentially the conceptual understanding, because sometimes the math is there, but it's all right. But the main goal here is just the electrostatic interaction. Right? So how is that going to be relevant? So suppose that we have a chemical reaction that is, do you mind if I switch screen now? Yeah, okay. So let's actually look at some simple interactions. So suppose that A is negatively charged, and then B that's reacting is also negatively charged. And whenever you have any chemical reaction, the first necessity really of any chemical reaction is they have to collide. They have to touch one another. But if you have negative charge that have to collide with another negative charge, naturally they will repel, right? So suppose that you have in solution 1 molar of A and 1 molar of B. I think B was a gas, but in any case, suppose that they're simply repulsive. If you actually look at them in solution, if you find out where A is located, if they're completely random, they're just going to be randomly distributed. Sometimes it's going to be close, sometimes it's going to be far, sometimes it's going to be, it's going to be random. But because A and B are repulsive in nature, you'll find, for example, that A is going to be just a little bit further away than compared to where B is going to be located, just because they have a natural repulsion. That is, because they're further away, A and B is not going to be able to touch each other as likely as you'd like. So their effective concentration goes down. So they're going to be further than randomness. So the effective concentration goes down. So far so good? Yeah. Just negative and negative. They don't like one another, so the effective concentration in solution is actually going to be lower than what you would expect them to be. So if the effective concentration is lower, goes down, is gamma going to be greater than 1, or is it going to be less than 1? What is our correction factor? So I have concentration of A times concentration of B. So this is ideal. But if I have to sneak in gamma, the activity of A, activity of B, is gamma going to be greater than 1 or less than 1? Less than 1, yeah. So the effective concentration is going to be less. So if I have 1 molars of A, but the effective concentration is actually going to be, say, 0.95 times 1 molar. So really it's 0.95 molar. Right, so lower effective concentration. That really is the basic. You can actually have, if you have a positive negative, you can actually get closer. And that's also true. So if they're opposite charges, that can also be true. But there's always a but. You can always make your, material, more complicated. The thing is, whenever you have a chemical reaction, you don't just have the two things that you're interested in. You're not just going to have A minus and B minus. You're going to have counter ions, you're going to have HCl, you're going to have NaCl, and so on. That's going to make our understanding of gamma a little bit more complicated, but more or less kind of the same too. And the theory that's kind of being worked on is called the Debye Huckle theory, or the Debye Huckle equation. And essentially the picture looks like this, right? So it's the same picture that we have before. We'll get into the equation in just a bit, but we're just going to go into just the basic understanding first. Now, in the Debye Huckle theory, though, you're going to assume not only that you have the materials that you're interested in, you also have excess, you have also other ions in solution. So for example, you have neutral, inert ion, I should say, not neutral. So you have Na plus that's not reacting. You may have Cl minus that's not reacting either. And the picture here is not going to look as similar as this, but it's actually going to be a little bit more annoying, which is, let me use a different page here. So suppose that in our solution, we have our simple reactions of weak acid is going to dissociate into A minus plus H plus. Yeah, for example, this is what we have. But in solution, you also have, say, Na plus, which is an inert ion. You also have a Cl minus in solution, which is also inert. So here you have A minus, you have H plus, you have Na plus, you have Cl minus. Everything is all intermixed together inside your solution. Now, if we go back to the picture that we had before, if I were to have an ion of A minus in solution, so this is my entire solution. Right, so this is in solution. On some occasion, you're going to have some H plus really close to it. Oops. But you can also have Na plus close to it. Just because there's always inert ion in there. So now the picture that we have is not just two interacting bodies, we have three. And in fact, if you have other ions in solution, you have 4, 5, 6, 7, 8, and so on. And in this case, the more sodium or chlorine inside your solution, which is basically inert, what you have now is a crowding effect. That is, suppose that our NaCl sodium chloride solution is actually a lot in solution. There's a lot of sodium ion. What happens is that the molecule that you're interested in is going to get shielded. This is obviously an exaggeration of the picture inside the solutions. The ion move around. This is a bit of an exaggeration. But what it is that in solution, the more inert ion that you have, the species of interest is now shielded. So majority of the time, in this case, what would happen to gamma? What is going to happen to the activity of A minus again? It is going to be less or more than it would be in solution now. Less or more? More or less? The answer is actually less. Because now suppose that we have another reaction. So this is going to collide with with H plus. But remember, the H plus ion is also going to be surrounded by inert ion, let's say Cl minus. Cl minus. So this is your inert ion in solution. So the molecule that you're interested in can't exactly collide as one another because now they have a shield layer of countercharge surrounding it that's kind of blocking it from actually reacting with the species of interest. So what you'll find is that majority of the time, your gamma, your activity, is going to be, most of the time, going to be less than 1. Just because this shielding effect happens once you have a lot of inert ion. Again, this is an exaggeration of what happens in solutions. Obviously, the ions are not touching, they're not crowding exactly like this, but the effect is about the same. Obviously, if this is like completely shielded like this, your activity coefficient is basically 0. But in actuality, there's gaps in the shield. Whoops, I erased a bit too much there, but you get the point. There's some gap that reaction can still happen. In actuality, your solution may more or less looks like that, right? So there's places that you can still collide. That's why even though the gamma is less than 1, it's not entirely 0. So before we go into look at the actual equation, there's several things that will affect how this crowding effect, how strong this crowding is going to be. So first of all, obviously, is you're going to have the more inert ion, more ion means going to be more shielding. That's going to be okay, right? So far so good. Because just because you have a lot more stuff blocking your species of interest. So yeah. Number 2, if your species have more charge, then you should also have more shielding. And what I meant by that is that suppose that I have a +1 charge, this is your species of interest, then it's not going to accumulate as much negative charge around it. Whereas if you have a 4 plus 4, you're actually going to accumulate much more negative charge, so you have a lot more shield around the species that you're interested in. Right, so that's what I meant by more charge. If you have a +4, then this shielding is going to be a lot more than if you were simply to have a +1 charge, for example. So far so good? Yeah. So let's see if you can guess this one. How about if your ionic size increases? Larger ion is going to be more shielding, or is it or less shielding? So that's my question to you. So suppose that we have comparatively 2 ion, both have a +2 charge. One of them is tiny, the other one is huge ion. Which one is going to have less shielding? The small or big? Big is going to have less shielding, right? Just because they're both the same charge, but now the +2, the minus charge is going to be able to agglomerate around it better. So let's just say the +2 ion accumulate around it 6 negative charge. If it's small, then this 6 negative charge is going to cover majority of the space around it. Whereas if you have a large ion, then the negative charge is going to be here, it's going to be there, going to be there, 4, 5, and 6. And you can see that there's more holes around the shield that you have. So it's going to have less shield. So larger ion, so this is point number 3 that I want to make. Larger ion is going to have less shield. All else being equal, of course. So far so good? All right. So if you kind of try to actually measure it, you will have the one that is posted on your class website in the laboratory, which is something like this. And just kind of going into some of our idea here, the numbers that we have here are the activity constant. So these are the gamma value. And I just kind of want to show that if you have more ionic strength, that means you have more ions in solution. As you increase the ionic strength, you have more and more ion. you can see that the number goes down, 9.67, 9.33, and all the way to 0.83. And the smaller, so this is large. This one here is large at 900 picometer. The first number here is 9.67, but as your ionic size gets smaller, the effect is going to get bigger, 9.64. It's going to be tiny, but it's going to be there. Or if you want to look at, when it's concentrated, 0.83, and as you go down, as the size gets smaller, the activity coefficients or the activities also go smaller. Right? It's just kind of how to read the data. And you can also kind of compare it too between, say, similar size ion but different charge. So here, if I were to go, let me use a different number, a different color here. My color is not working. So let's look at the 600. So this is going to be a +1 charge, is going to be 965. But if your charge is +2, at 600 picometer, your activity is going to go down as well. Again, it's just because you have more charge, so it's going to gather inert ion around it better, so it's going to have a little bit more shields around it. So the activity goes down. And the thing that you remember is just the activity more or less goes down. Now that's just kind of the conceptual. And any questions so far? No? Yeah? So the rest is just a little bit of plug and chug, because I'm not going to try to derive the Debye Huckle equation. But this is the one that I want you to write down on your note. Right. And I try to match it with the notation that you have in the lab manual as well. There's a little bit of missing line there. So the first equation that you want to know is how the activity coefficient is actually related. And the mathematical number that you want to write down is something like this. The log base 10 of the activity coefficient is -0.51 times z squared times mu. By the way, what is mu in this case from your lab? Ionic strength. Thank you. So in this case, mu is the ionic strength. Z is going to be the ionic charge. Again, the larger, the higher the charge, the bigger the shielding is going to be. And then the next one here, we also have alpha. This is going to be the radius, ionic radius. Okay. So that's kind of the gamma. And specifically though, majority of the time we're going to be using this equation. This ionic radius is going to be in unit of picometer. Essentially, whatever you saw in that particular table, it says 600 picometer, then that's the number that you want to use. And if one were to try to draw what the graph looked like, more or less it looks something like that. I just grabbed this off directly from Wikipedia, so that's right too. It's just the behavior. If you will compare these two graphs, the one on the top versus the one on the bottom, this is going to be in the bottom have smaller charge. And then here, the one in the bottom, at the very, very bottom, you have larger charge. So, oh, my bad, smaller size. And this smaller size and then larger charge as well. Right. So the effect is going to be the same as what you've seen from the picture before. Sometimes it's math, sometimes it's just your imagination. They get closer, they get further away, they have more shielding or less. And essentially, if you kind of do all calculations, the more complicated the equation that you have, sometimes it's just a good idea to just kind of step back and just figure out I'm expecting this number to be less than 1 or bigger than 1. And if you see it the other way around, usually you probably make some kind of calculation error. Sometimes it's just a formality of what you kind of understand. So you guys written down this equation, yeah? As well as the ionic strength equation, yeah? Okay. So what I want to do for it now is try to do an actual sample equations or calculation, and we're going to do an example that you have from your lab manual, just because it's something that you've already done before, and it makes it a bit easier to go through it. Oh, the other thing that I want to mention is that the log, this is written log base 10. So you kind of have to do 10 to the power of whatever it is to get the actual activity coefficient. The last one that I want to mention before we go into the actual calculation is just go into this ionic radius itself. So this is your KHP molecule that you have. And these are just kind of some of the geometrical size that you have. So for example, if you have a benzene molecule, which is just this whole thing, there's a hydrogen sticking out, so carbon-hydrogen bond is 109 picometer. Then the carbon-carbon bond between here is 139. So if you actually look at the geometry, you'll find that the size from top to bottom here, from here to here, is going to be about 278. And then there's a bit of hydrogen sticking out, so this is going to be 109. And then you're going to have a carbon-carbon bond, which is about 140. I'm just rounding it out. And then this last one here is about 70 picometer and so on. So if you simply add them up together, we have 100 plus 300. Again, I'm just rounding out. Plus 150 plus 50-ish. So if you add everything up together, you get exactly 600 picometer, and that's the number that you were supposed to choose or use when using or finding the ionic size of KHP. It's just how big the molecule is going to be your ionic radius. Obviously, this is not spherical, but if your molecule is spinning around in 3 dimensions, it becomes an effective sphere. So if you don't have any information in terms of what ion that you're actually using, you can actually just kind of estimate the size just by calculating all the bonds and how long they are and how big the molecules are going to be. So it's actually fairly straightforward in terms of the calculation that we're using. So in KHP, we're using 600 picometer. So let's just do some actual example calculation. And we're just going to do the 95% equivalence volume. But instead of writing everything down in terms of equivalence volume, I just kind of want you guys to look at it in terms of what we actually have inside our solution. So this is our beaker. Actually, this beaker doesn't have an arrow on the top. So this is our beaker. In this particular problem, what we have is potassium ion, some K plus ion, and the concentration of K plus ion is going to be 0.0168 molar. We also have inside our solution, again, there's some calculations, limiting reactant, theoretical yield, acid-base reaction, but for now, I just want to get rid of those fundamental equations or reactions, but just look at the species that we have in solution. So inside the solution, we also have a sodium ion, which is inert. In this case, we have 0.0160 molar. We also have HP minus, which is this one, by the way, which is this whole thing minus the K plus. So that's our HP minus. Actually, it's better if I just kind of try to draw it later. So it looks more or less like. Actually, I don't remember what it looks like. I think it looks something like this. So this is our HP minus. That doesn't look right to me, but close enough. And the concentration of HP minus at 95% equivalent volume from your laboratory is 0.00084 molar. And the last one, we also have HP2 minus, which is 0.01060 molar. And that's the molecule that 2 of the hydrogen is going to disappear. That's kind of my squiggly thing. So this is all the species that we have in the solution. The reaction that we're actually interested in looking at is HP minus in equilibrium with H plus P2 minus. Yep. And in this particular case, we're going to have make a bit of the assumption that this concentration is going to be small. And the reason it's small is because KHP is a weak acid, so the rate of this disproportionation is going to be less than 1%. So you're going to have less than 1% less than 0.0084 molar, so which is going to be pretty tiny. So for our simplicity, we're just not going to calculate it. Although if you want, you can put it in there, but we don't have to, just because it's going to have like 2 more zeros behind the decimal point, so it's going to be less. In terms of the calculation that we have to do, is the first thing that we want to know is we want to plug it into the equation that we have earlier, which is this Debye Huckle equation. So first we need to know what is the ionic strength first, right? The ionic strength is just 1/2 times this concentration times the charges square. So let me go on to the next one here. I'm just going to put a table. So contribution to the ionic strength is that we're going to have the charge times the concentration of the molecule. So K plus is going to contribute 0.0168. I'm going to put this as a unitless quantity times the charge of potassium ion is 1, so it's going to be 1 to the power of 2. So again, mu is the sum of the concentration of species I times the charge of species I to the power of 2. So that's 1 to the power of 2, and the concentration 1.68. For Na plus, 0.0160 times 1 to the power of 2. HP minus is going to be 0.00084 times the charge is minus 1 to the power of 2, so it's going to be 1 to the power of 2 as well. And because it's negative to the power of 2 is just positive, we don't really care about the sign. And the last one is P2 minus is going to be 0.0160 times 2, or I should say negative 2 to the power of 2. And in order to find out the ionic strength, we simply have to add everything together and divide it by half. Half times the sum of what we have it here on the top. So let's just do the calculation really quickly. Do you guys want me to go to the calculations or not really? Or you've already done it? I think you guys are okay with it. All right. Well, let's say it's just a refresher for now, because you guys haven't seen it in a while, at least 3 weeks. So what you'll find is that the sum of this whole number is going to give you if you look at the sum on its own, it's going to be 0.04964. So that's going to be the sum. And don't forget to get the actual ionic strength, you have to divide this by 2. So this is going to be 0.02482. Anybody got a different number than I do? And just kind of always double check, because it doesn't hurt. Oh, actually I got 9764. Sorry, 97. Sorry about that. Like I said, always double check the number. So the ionic strength in this case is going to be half of the sum, so 0.04882. If you got the first answer, you forgot to put this to the power 2. That's my guess. So that's what I did wrong before. I forgot to put 2 to the power 2. So everybody make mistake. So let's actually try to calculate the gamma, or the ionic strength, for the species that we're actually interested in. So we're going to try to figure out the gammas of each one of these. And it should, in the end, go pretty close to the value that you have calculated, or you've tried to fit from the graph. So the equation again is log of the activity. I'm going to use HP minus now, for now, is going to be equal to negative 0.51 times the charge z to the power of 2, which is 1, I should say negative 1 to the power of 2, times the square root of mu divided by 1 plus alpha, which is the atomic size, which is 600 picometer. Again, this whole thing is going to be a unitless quantity, divided by 305 times the square root of mu. Let me just double check that I have the right equation. Yeah, that's about right. So this is the information that we have. So if one were to try to calculate everything here, we know that the ionic strength, based on the value that we get here, is going to be 0.4882, 0.4882. So let's just try to put all the numbers together. Yes, thank you. This is where I usually just put everything in Excel. Okay, so by the way, the square root of this number is going to give us 0.6987, just for simplicity. Times 0.51 divided by 1 plus 600 times 0.6987 divided by 305. So log of gamma, the activity coefficients of HP minus, is going to give us negative 0.1501, essentially. Can you guys double check my number, please? You guys got the same number? No? What do you get? 0.07. Let's double check again. 0.51 times the square root of 0.04882. So let's try to do this one step at a time. So negative 0.112686 divided by 1 plus 600 divided by 305 times the square root of 0.04882. This is going to be 1.43466. So if one were to divide one with the other, oh, 0.0785454. Okay, so I think this is actually the right number. And in order to actually get the activity coefficients of HP minus, I'm going to do 10 to the negative of the log that I calculated to get rid of it. So negative 0.0785454. And you should get in the end 0.83455 for your activity coefficient. Yeah, that's pretty close to what you should get in the laboratory as well. Now, while we're at it, we're going to try to calculate the activity coefficient of the HP2 minus. So log of activity coefficients of P2 minus is going to be pretty similar, but this is going to be negative 0.51 times 2 to the power of 2 times the square root of mu divided by 1 plus 600 divided by 305 plus the square root of mu. And notice that the only difference here is just the number 1 to the power of 2 versus 2 to the power of 2. So I know for sure that this is going to be 4 times larger. Log gamma P2 minus is going to be 4 times larger, which is going to be 4 times 0.0785454. So it's going to be 0.314181. Yep, I'm not doing anything odd. So far so good. So gamma P2 minus is going to be, should be, a smaller number. Sorry, I keep forgetting to put the negative sign in there. So this is going to be 10 to the power of negative 0.314181. This one is actually slightly different than what you have. Yeah, but that's all right. So let's try to see if the number actually matches with what we have. Keep that in mind, 0.8 and 0.5 essentially. And we'll just kind of look at the table for the charges that we have. You guys are done with the calculation? Yeah, okay. Let's go over. So we're going to look at from our table the activity coefficient. HP minus is going to be plus 1. And we want to have an ionic strength of, I forgot what the ionic strength was again. So 0.0488. So 0.048. So HP minus is at 600 picometer, and we're close to 0.05. So we're about 0.854. And then P2 minus is going to be charge of plus minus 2, and then the number that we get 0.854. Right? And that's more or less kind of exactly what we have, with some changes. For one, we're not exactly at 0.05 ionic strength, right? So we're not exactly here, but close enough. And that's what we have. Any questions before I wrap up the class? Because I think we're pretty close to the end. Last minute questions? No? No, no, no. Yeah. Did Dr. Probisco send you guys what will happen after Thanksgiving? In terms of, will you guys cover electrochemistry or
She planned on, yeah.
plan on that?
She said that was supposed to be the last week.
Okay. So, do you guys remember how to find out the oxidation number of a molecule? So, in our last 3 minutes, I'm just going to go into the oxidation number because that's one of the things that you need to know for electrochemistry. And the reason why you want to know the oxidation number is because electrons in electrochemical reactions, electrons are actually going to get sloshed around between one atom to the next, and you keep track of it by looking at the electrochemical or the electrochemistry or the oxidation number changes. This is a quick oxidation number thing for you to note. So this is more or less the periodic table. So I have 1, 2, 3, 4, 5. So that's more or less the periodic table. So if I were having a hydrogen and it's binded to another molecule, what's the charge, the most likely charge on hydrogen is +1. How about on the next one? The next one over here, aluminum and so on? Nope, +3. And then the next one here, for carbon, carbon is on the fourth one here. It's going to be, the most likely charge is going to be plus and minus 4. Okay. The next one is going to be -3, -2, -1. That's not mine. Okay. And then noble gases is going to be 0. Okay. So when you're looking for oxidation number, this is a pretty good guide in terms of what you're going to have. So for example, hydrogen is going to most likely to have a +1 charge. Calcium, which is over here somewhere, is going to have most likely a +2 charge. Carbon can have somewhere, anywhere between -4 all the way to +4. So which is why carbon is kind of a bit more annoying. So you can have anything to -3, -2, +1, +2, and so on, anywhere between -4 to +4. And the rest is -3, -2, -1, 0. Now, the oxidation number simply tells you whether the molecule is gaining electron or losing electron. So if you have, for example, an HF molecule, what's going to be the oxidation number on hydrogen, and what's going to be the oxidation number of fluorine? Good, thank you. Hydrogen is here, +1, and fluorine is going to be -1 because fluorine is right here in the periodic table. And what you'll find is that the sum of the oxidation number is going to be 0, or equals to the charge of the molecule. So for example, HF is going to be +1, -1. So carbon, for example, if I were to have CH4, the oxidation number on the hydrogen is going to be +1 each. So the oxidation number on the carbon is going to be a -4, right? And I got that because oxidation number of one hydrogen is 1 each, so +4. And if you so if you're trying to solve for the oxidation number of carbon here, which is X, it's just 1 plus 1 times 4 is going to be equal to 0 because the sum charge of CH4 is 0. So X is going to be a -4. So that's kind of more or less how to solve for the oxidation number. Carbon is the one that's hard to kind of guess just because it can be anywhere between +1 to minus 4 to plus 4. So it's going to be a wide variety, as well as the transition metal. That's the other one that you have to solve as well. And more or less, what you have to do is just solve for x. So one last bit before I leave. Um, the whole charge is going to be equal to the total charge of your molecule. So for example, if I were to have an NH4 plus, what's going to be the oxidation number of nitrogen? It's going to be minus 3. And we get minus 3 because if I were to simply put X as the oxidation number of nitrogen, X plus each of the hydrogen is going to be plus 1. So 1 times 4 is going to be equals to the sum of the charge. So it's going to be plus 1. So X is going to be 4. X plus 4 is equals to 1. So X is going to be 1 minus 4, which is minus 3, which is equals to what you have for the nitrogen. Okay, so these are the most likely charges, and I'm sure Dr. Probisco will add a little bit here and there, some caveat when it's not true. All right, see you guys later, or some of you anyway, and